Thank you again, Susan, for the introduction. So we're going to be covering regular expressions with Linux tools. So let me go ahead and just going to share my browser first. So if you want to follow along, we do have a GitHub repo that contains all of the examples that I go through today in the presentation. And you can either create a clone of the repo and execute the exercises there, or you can scroll all the way down to the bottom here and you'll see a link that says Launch Binder. And if you do that, that will open up a Jupyter Lab session for you, where you can find all of the repo content. And I would suggest that you could go to the examples.sh file, and that contains all of the commands that I'm going to be using today. Mostly grep, but a few examples with awk and sed. So if you want, you could just cut and paste these over into a terminal. So with that, I'm going to stop sharing. I'm going to switch over to my slides. And we have a pretty small group today, so I'm going to keep things as usual, a little informal. I will be checking the chat periodically to see if there are any questions. Okay, and can somebody just confirm now that you are seeing my title slide?
Yes, we are.
Yes, I am.
Okay, great. All right. So let me just go ahead and minimize that. All right, so again, in the chat, we have links to the PowerPoint slides. You could find those in the bit.ly complex link that takes you to a directory of PDFs. And then the examples, again, are in the SCSE complex regular expressions repo. So a little bit about Complex, just a reminder that this is an NSF-funded program where we're teaching what we consider the non-programming skills to effectively use supercomputers. And the topics include parallel computing concepts, Linux tools, bash scripting, security, batch computing, how to get help, data management, and interactive computing. So a quick introduction. If you're not familiar with regular expressions, they provide a way to identify strings that match a specified pattern in a body of text. They have their foundation in formal languages and theoretical computer science, and we'll talk about that very, very briefly today. Now, at first glance, the regex formalism may seem a little daunting, but they do have very practical applications for computational and data scientists. And then in practice, the implementation of regular expressions in computer languages, text editors, and Linux utilities, it goes well beyond the original definition to allow for more complex patterns and even things like back references. So while the syntax and the feature set for regexes can vary across languages, they'll look a little bit different, say using Linux tools or in Java or in Perl or in Python. The basic concepts are universal. But in this tutorial, we're going to focus on their implementation in the Linux utilities such as awk and sed and grep. So why do you need to understand regular expressions? So I'm going to say you can get by without regexes, but knowing how to use them can make your life much easier, especially when you combine it with the Linux tools awk, sed, and grep. So I think this audience is composed, I'm going to say, of two main groups, data scientists and computational scientists. So if you're a data scientist, you're going to spend a lot of your time performing mundane tasks to filter your data, get into usable form. This is the part of what we call ETL, extract, transform, and I forget what the L stands for, and load. So regexes allow you to create more compact and robust scripts. If you're a computational scientist, say somebody who's doing simulations, Regexes are going to be really helpful when extracting important information from the results of your simulations, or when preparing input files for, say, high throughput computing workloads. And I'm going to say this is going to be, we're going to try to make it a gentle introduction to regular expressions. Entire books have been written on the topic. In fact, about 15 years ago, I worked my way through the O'Reilly book on mastering regular expressions. It can go really, really deep. We can't cover everything in regexes in 1 hour. You could literally spend days, maybe even weeks or months going really, really deep into regular expressions. If you manage to get a hold of a copy of this book, and I know most of us don't go to the O'Reilly books anymore since there's so much available online, you'll see that the author had put together a regular expression that literally filled an entire page. So we're not going to go that deep. We're going to try to cover just the basics. I think what you need to satisfy most of what you will be doing with regular expressions. So a few prerequisites. You're going to get more out of this session if you're already familiar with the tools that use pattern matching, such as grep and sed and awk. If you're not familiar with these already, I'm going to say maybe go back, take a look at the PowerPoint slides and the GitHub repo for Linux tools. But even if you don't have the background, stick around. I think it will be a nice introduction. And then once you go through the notes on Linux tools, I think you could go back and really explore these topics a little more deeply. All right, so we're going to start off with the regex formalism. So this is the way computer scientists will talk. They'll say that a regular language is a formal language that can be defined by a regular expression. I know that's very, very roundabout, and it has the following definition over an alphabet that we denote as sigma. So we have the empty language as a regular language. That's actually going to be important because our matches can sometimes involve empty strings. For every character that's an element of that language, what we call the singleton language, that's a regular language. So again, here the implication is that some of our matches can sometimes be as simple as a single character. If A is a regular language, A star, where the star is the Kleene star, is also a regular language, and we'll be talking about this a little bit later in the workshop. If A and B are regular languages, then the union and the concatenation are regular languages, and no other languages over sigma are regular. So what we're going to do today, though, is we're going to make that a little more practical. So unless you do theoretical computer science or linguistics, you're generally not going to start with the regex formalism. Instead, you're going to work with regular expression engines that provide an augmented syntax for constructing regular patterns. So this table summarizes what I think are, most of the key features of regular expressions. There's a few of the more advanced topics that I'm not including here. Think the syntax for, say, backtracking and lazy matching, which we won't have time to get into today. But this is kind of an overview of all of the key elements of regular expressions. We're going to be spending a lot of time looking at quantifiers. We have the star, the question mark, the plus, and then what we call these curly brace notations with either 1 or 2 arguments. We have a wildcard, which is denoted by a period. We have anchors, caret and $sign. We have ways for specifying multiple characters and negation of those groups of characters. We'll look at character classes, say for defining uppercase letters, lowercase letters, digits, white space, and so on. We have parentheses for grouping, and finally a vertical bar for alternation. And so just a few more words about grep before we dive in. So we're going to be starting off with grep, which I think is the simplest Linux utility that does pattern matching. Grep returns all the lines from a file that match a given pattern. It can be more instructive though to see what portion of the line results in the match. And to do this, we're going to configure grep to colorize the output. The default is going to be bold red. Now, if you're working on expanse, we already have grep alias to grep dash dash color equals auto. If you're working in the if you had launched Jupyter Labs, say through MyBinder, or you're working on a different system, you may want to add this line, alias grep equals grep dash dash color auto. You can set the color to something other than red. I know that there's a good chance that a few of you might be colorblind or color impaired. So if red doesn't work for you, you can set a different color. And one last note, throughout this presentation, grep matches are going to be underlined to emphasize white space captured by the match, but this is not a feature of grep. So we're going to start off with the very, very simplest regular expression, and that is just a literal string. And this is something, if you've used grep before, that you've probably done already. And I'm going to point out here, though, that the grep matches are case sensitive. So let's take a look at a file, fruit.txt. A lot of my examples involve fruits, and you'll see that it has, about 10 lines, where each line contains the names of 3 fruits. And one thing to point out here is that we have banana in both uppercase and, capitalized and all lowercase. So starting off with a couple very, very simple grep commands, we're first going to search for banana, all lowercase and fruit.txt. So we do grep banana fruit.txt, and we see our 2 matches are apple banana pear and cherry banana peach. But notice though that we didn't match banana capitalized, and in our second grep command we have grep banana with an uppercase B fruit.txt, and then again 2 matches, and both of these included banana capitalized. And just a reminder that the underlining is not part of the grep output. I just added that to make it a little bit easier to see the output and see the entire context of the match. And also as a reminder, if you're following along, all of these examples are in the GitHub repo. So both the commands in the examples.sh file and all of the input files that you'll need to run these examples. So if we want to make a choice of multiple characters, we have a couple of ways we could do this. So first, grep has an option -I to make the matches case insensitive. Now, sometimes this is what you want, but there might be unintended consequences. I don't have it in this example, but let's look at that first grep command. We have a grep-I banana, and this is going to match banana all lowercase and banana with an uppercase B. But if our file contained other mixes of upper and lowercase letters, say banana in all uppercase, or BAN all uppercase, ANA all lowercase, and so on, we're going to get all of those matches. So now we're looking in the next grep command at our first real regex feature, and that's using those square brackets to match a collection of characters. So here we specified lowercase b and uppercase b, followed by banana, and you can see that we picked up banana, all lowercase, and banana capitalized. So the difference between these two is that the second case wouldn't have picked up these other mixes of upper and lowercase letters. It's going to be much more specific. So we're going to go into that in more detail. Let me just take a look at the chat real quick. Question from Randy. Would that second grep capture lowercase b, uppercase b, ANA? No, it wouldn't. It's only going to capture, let me go back here. See if I can. So I'm having a, yeah, there we go. No, it's only going to pick up a lowercase b or an uppercase b, followed by the string a in all lowercase. All right, so we're going to generalize that previous example a little bit, where we specify an arbitrary set of characters that satisfy a match. So we're going to be looking at the file ash.txt, which can consist of words beginning with character followed by ASH. So we can see that we have bash, cache, dash, gash, hash, and so on. And then at the end, we have hyphen ASH. So in the first example, we're going to match the characters B, D, R, or W followed by ash. So we took those, we enclosed those in the square brackets, and we get bash, dash, rash, and wash. And then we can invert the match. Here we're going to put a caret be before the BDRW, and this is going to mean we're going to match any character except BD, R, or W. So in this case, we picked up cache, gash, hash, lash, mash, and hyphen ash. Now we can also specify a range of characters using a hyphen, so with the syntax x-y. And like in the previous example, the caret is going to indicate negation, and if you want to match a literal hyphen, make it the first or the last character. So in our three examples, first case, we're going to look at a range of characters, the letter lowercase d through lowercase h, followed by ash. You can see we pick up the three matches. In the next case, we're going to use the caret to indicate negation. So now we're going to get any character except lowercase c through lowercase r, followed by ash. And then in the last example, we show how we can include a literal dash. So we're here going to match a dash or the letters G through L followed by ash. And you can see the output here. And again, if you are following along, either by in Jupyter Lab that you launched by clicking on the My Binder link or on Expanse or your local device, all of these examples are in the examples.sh file. All right, so regex also recognizes the standard POSIX character classes. I use these sometimes. So there are character classes for lowercase letters, uppercase letters, alphanumerics. That's the third example, the colon alpha colon. We have a character class for digits. We have one for alphanumeric characters. So that's going to be all numbers or digits, and for punctuation. Now I find that in real life that I tend to just use the notation A-Z or capital A dash capital Z 0 through 9 or so on. I find a little more convenient than using the POSIX character classes, but they're there if you need them. Now what I find particularly useful though are things like the space and the punctuation classes. So I remember I worked on one project where I was trying to match punctuations, and this was some time ago before I knew that there was a punctuation class. So I, used my square brackets and I, worked my way down the keyboard. I had period and comma and semicolon and colon and question mark and so on. But inevitably, there would be something that I would have missed. So if I use the punct or punctuation character class, I will pick all of those up and I don't need to search over the entire keyboard to make sure that I matched all of the possibilities. Now, just a word about syntax, and this is something that you might find a little confusing. The character class is defined by square bracket colon, the name, colon, square bracket. But you'll notice in all of our examples that we have two pairs of square brackets. So for example, left bracket, colon, lower colon, right bracket. And the reason is, and here I think that the syntax is just a little confusing. Those brackets are being used in two different ways. The outer set of brackets is being used to define a set of characters that are going to match, And the inner part, the inner pair of brackets is part of the definition of the character class. So, like I said, this could be a little confusing, but I think it becomes a little clearer if you think of each of those character classes as being expanded out to that list of characters, which is then enclosed within those outer square brackets. And notice though, that with the syntax, I could specify more complex combination of characters. So let's say that I wanted to, in the left example, match any lowercase letter or the digit 3 followed by OOT. So here I'm going to have my outer pair of square brackets, and then I'm going to have bracket colon lower colon bracket 3, and then closing bracket. We can see on the right that I was able to use two POSIX character classes, the class of punctuations and the class of digits. And here's a breakdown of some of the common character classes. And again, I find punctuation, blank, and space to be particularly helpful. All right, next we're going to move on to wildcards. A single dot matches any character except a new line. Sorry, let me just. So it's going to match any character except a new line. So let's look at that first example. We have B dot 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 A fruit dot text. So this is going to match any string consistent of a B followed by any 4 characters except new lines followed by A. So as we might expect from our fruit.text example, that's going to pick up apple, banana, pear, cherry, banana, peach. In the next example, I match any character followed by an E, any 2 characters, and then followed by an H. So here we pick up all the lines that contain peach. And then in the third example, I have dot EA dot. So that's going to match any character followed by EA, again followed by any character. And here we're going to pick up pear and the first 4 letters of peach. And I also want to point out with grep that when we use regular expressions in this way, if there are multiple matches in a line, both of them are going to be returned. So in that second last line of output, we matched pear, and we also matched the first 4 characters of peach. All right, so now we're going to move on to quantifiers. And this is where I feel like we're really diving into regular expressions. So everything we've done up to this point involved matches of fixed length. Now, quantifiers allow variable length matches, and this is where regular expressions get so much more flexible. So the list of quantifiers we're going to be working with are the star, which means 0 or more of the preceding element. A plus sign means 1 or more. Question mark, 0 or 1. And then if we have curly braces and a single integer, that means we're going to be matching exactly n of the preceding element. If we have in our curly braces an integer followed by a comma, that means we're going to be matching at least that many. So in this case, at least n min. If we have comma n max, it means at most n max. And if we specify 2 integers, in this case, curly brace n min comma n max, is going to mean anywhere from n min to n max of the preceding element. So let's look at a few examples. And then after this, I'm going to check the chat, see if there are any questions. So in the first column, we have our grep command with the regular expression, and in the right column, the interpretation. So we're going to start off grep dash capital E and single quotes A, B star C and searching the file abc.txt. So this means we're going to be looking for A followed by 0 or more B's followed by C. In the next example, we'll replace the star with a plus sign. So now we have A, B plus C. This means A followed by 1 or more B's followed by C. So notice the distinction between those first 2. In the first case, it was 0 or more. In the second case, it was 1 or more. In the third example, we use a question mark instead. And this means we're looking for exactly 0 or 1 Bs. And then in the next four rows, we look at the matches using that curly brace notation. So looking for A followed by exactly 3 Bs, 3 or more Bs. That's a case where we have 3 comma, but we don't specify an upper bound. Up to 3 Bs, and then finally exactly 3, 4, or 5 Bs, again followed by the C. So looking at the examples, so we're going to be working with the file abc.txt, and you'll see that it has six records containing anywhere from 0 to 5 Bs. So we have AC, ABC, and so on. So demonstrating these, if we kick off with a grep -E, A, B, star C, you see that we're going to match all of the lines in that file because we can be matching anywhere from 0 to an arbitrary number of Bs. So all of those records are going to match. The second example, if we drop down to AB plus C, we can see that we're going to match the second line onward. So A followed by at least 1 B. In the third example, AB question mark C, we're going to match AC and ABC. So again, A followed by exactly 0 or 1 Bs. And then in the right-hand column, we look at a few examples with the curly brace notation, starting off with A followed by at least 3 Bs, up to 3 Bs, and then exactly 3 to 5 Bs. So I introduced a little bit of new syntax there. We started using single quotes around irregular expressions, and we added the -E option. So we should take some time to explain that. So regular expressions can come in multiple flavors. So there's what we call the basic regular expressions, extended regular expressions, and Perl-compatible regular expressions. By default, grep uses the basic flavor, which requires that the following characters be preceded by backslashes. The parentheses, the curly braces, the plus sign, the question mark, and the vertical bar, which we'll get into shortly. So, for example, if we wanted to match A followed by anywhere from 3 to 5 Bs followed by C, if we're using basic regular expressions or BREs, we would have had to precede those curly braces with backslashes. So this is a little bit harder to read. If I use the -E option, that tells grep to use extended regular expressions which don't need the backslashes. So now we could write that simply as AB, and in curly braces, 3, 5, C. And the single quotes around all of that prevent the Linux shell from interpreting the special characters so that they're passed to grep. So let me just take a look here real quick, see if there's if there are any questions.
We don't have any.
Nothing in chat. Okay, good. I will go back to the presentation again. All right, so if you go back to near the beginning of the presentation when we talked about the regex formalism, they didn't mention anything about curly braces or plus signs or question marks. So that wasn't part of the original regular expression definition. But I did mention also, though, that these implementations of regular expression engines use a richer syntax so that we can so that it's easier to write clean, readable regexes. Now, note though that we really don't need the plus sign, the question mark, and the curly braces. So in the first column here, I'm showing our original regular expressions. And then in the second column, I'm showing how we could have done that same thing using only this.
We can't see your screen.
Oh, I'm sorry. I didn't share again. Thank you. Okay. You should all be seeing my screen. Wait, hold on. Continue to share. Seeing my screen again?
Yes.
Okay, great.
Uh-huh.
Sorry about that. Um, and thank you. I forget who chimed in. That thank you so much. Instead of waiting until I got 10 more slides into the presentation. So what I'm showing here is how we could have written those regular expressions using only the asterisk and the vertical bar for alternation, which we'll be talking about very shortly. So the first column has our original regular expressions. The second one, we use only the star quantifier and alternation. So of course the first regex is going to be exactly the same, a, b star, c. And the next example, um, where the plus sign means one or more, here we used A, B, B star, C. So that first B means that we're going to have at least one B as part of our match. And then the B star means zero or more B's. So we combine them and we get one or more. If we do A, B question mark C, so that means zero or one B's, we could use alternation. So we can look explicitly case AC and at the case ABC. When we get into the curly braces, it gets a little more complicated. So if we wanted to match exactly three B's, that's not too hard. It's going to be A. We explicitly write out the three B's followed by the C. If we want three or more B's, that's going to be similar to our second row, where we're going to explicitly write out three B's so that we're matching at least three, and then followed by B star. And then when we look at the case of up to three B's, now we need to start using alternation. So we match AC, ABC, ABBC, ABBBC. And then finally for the case of exactly 3 to 5, we're going to write out the three cases of A followed by 3 B's, 4 B's, or 5 B's, followed by a C. And again, all combined using the alternation. So again, you don't really need the plus, the question mark, the curly braces, but life is so much easier if you do use these. Quick side, I mentioned earlier that the star is actually called the Kleene star. This was named after the American mathematician Stephen Cole Kleene, and it really is pronounced Kleene. You look at it, you might think clean, but it is Kleene. So your computer science friends, I think, will be impressed if you know this, but if you call it a star or an asterisk, everybody's still going to know what you're talking about. Okay, getting back to quantifiers. Something that you might not have thought about is that quantifiers are greedy, and they're going to always look for the longest possible match. So in the example below, we start scanning the line from the left until we find the first P, and then from the right until we find the first R. And I have a note here. It's a little more complicated than that. Regexes do this thing called backtracking or implemented through finite state machines. But in this case, if we only have one quantifier, this is a close enough working explanation. So looking at our fruit file again, remember we have about 10 lines containing each the names of 3 fruits. So here we're going to do a search. Grep p.star r fruit.text. So this is going to mean that we're going to look for a p followed by 0 or more of any characters. So recall that the dot is the wildcard that matches everything except a new line, followed by an R. So we're going to get matches like the first P in apple through the last R in pear. Or, in the third line, the first P in pear through the first R in grape. So in each of these cases, it was the longest possible match that was returned. And a little bit later, we're going to contrast this to what we call lazy matching. Okay, next topic I want to cover is grouping. So if you recall, and hopefully I said this right earlier, is I didn't say that the quantifier applied to the previous character, but rather it applied to the previous element. So regexes can group multiple characters into a single element using parentheses. So we're now going to look at the file grp.txt, or for group.txt, and there's some, seemingly random strings in there. 3 zeros, an A, a B, and then 3 ones. But you'll notice in each successive line that we add multiple copies of the string XYZ in between the A and the B. So we have an A, XYZ, B, A, XYZ, XYZ, B, and so on. Well, I see a question here in the chat. Oh, just
It was just me.
Thank you already. So, if we wanted to match, say, A followed by 0 or 1 XYZs, or 2 or 3 instances of XYZ, it would be a little awkward, a little hard to do this if we didn't have a way to group characters together. So here we're going to use those parentheses so that we treat XYZ as a single element. So in the first grep command, we have A, and then in parentheses, XYZ question mark B. So now we're going to be looking for those strings that contain an A followed by exactly 0 or 1 instances of XYZ. In the next case, we're going to look for 2 or 3 instances of it. And in the last example, we're going to look for A followed by at least 1 instance of XYZ, and then followed by B. So again, you strictly don't need these parentheses, but think about how you would have written this using just alternation and that the Claney started doing. It would have been much longer, much more likely that you would have made an error putting it together. All right, anchors. Another really useful feature. Without any other specifications, grep is going to look for a match anywhere in the line. And anchors allow us to restrict the matches to the start using the caret or the end of a line using a $sign. So going back to our fruit.txt example again, first search is just going to be for pair in fruit.txt. And you can see that we returned 5 matches. Those first 2 lines have pair at the end, the next 2 pair at the beginning, and last one pair at the start. And then in the next grep command, we do a caret pair, which means that we're just going to be looking for pair at the start of the line. And here we'll return those 2 matches, pair followed by kumquat grape or peach kiwi. And then finally, last example, we have pair $, which means we're going to be looking just for pair that occurs at the end of the line. So, when I started writing regular expressions, I had a hard time keeping track. When do I use the $? When do I use a caret? Which means start of the end, which means start of the line, which means the end of the line. And for me, kind of the mnemonic was, I thought carets are cheaper than dollars. So I'm going to use a caret first, say at the start, a $, at the end. I don't know if that mnemonic will work for you, but it kind of stuck for me. All right, next feature is something called alternation. Sometimes we want a single regex that matches 2 or more patterns, such as a string that appears at the start or the end of the line. And we've seen alternation already when we looked at alternatives to using the full set of quantifiers. So we just saw examples with anchors. We had our caret pair, we had our pair $. In the last example, though, we combined those using a vertical bar, and our regular expression is caret pair, vertical bar, meaning or, and then followed by pair $. In this case, we pick up the lines with pair at the beginning and pair at the end of the line. Now, word boundaries. This is a, how would I put it? This is something that could be a little difficult without using a bit more syntax, or say using the quantifiers and the features that we've seen so far. So we're going to work through an example. It's going to be a little complicated. You don't need to pay attention too carefully because I'm just doing this to illustrate how difficult it would be to do one of these matches without word boundaries. And then when we're all done, we're going to see how we could do this the easy way with grep. And we're going to be looking at what seems like it should be a really simple example. We're going to try to find lines that contain a valid 5-digit zip code. So we're going to start off doing this the hard way. Let's look at the file zip.txt. And you'll see that there's a bunch of lines in there that contain valid and invalid zip codes. So if we have a string of 5 digits, we'll call that a valid zip code. So we start off 12345 is valid zip code 12345 is valid, and so on. We have a line that contains just the zip code, and then at the bottom we have some invalid zip codes. So the first case, 123456, zip code is too long. Now there is a valid zip code in there, the string 12345, but also 23456 would be a valid zip code, but it's ambiguous. We're going to say that's invalid. Next case is pretty easy. The zip code is too short. And then we have a couple of zip codes where there's a letter tacked on, A12345 or 12345B. And we're going to say those are invalid. Now, if we just do a naive search for a string of 5 digits, you'll see that we pick up all of the valid zip codes, but we also pick up most of the incorrect ones. So I would say those last 3 matches, those are false positives. I wouldn't consider 12345 or A12345 or 12345 to be valid. So what we're going to do is we're going to put together a complex regular expression where we look at all of the different possibilities. 5 digits at the start of the line, followed by punctuation or white space. 5 digits preceded by punctuation or white space, followed again by punctuation or white space. 5 digits at the end of the line, preceded by punctuation or white space, and finally a line consisting of exactly 5 digits. So I do this, and you can see now we only picked up the valid zip codes. But you'll notice, though, that we also picked up some extra text, and this is why I'm using the underlining. In the second line, notice that our match is space 12345. In the match after that, we get space 12345, comma, and then next one is space 12345. So we got rid of all of our false positives. We returned all the lines that contained a valid zip code. But if we're looking for just the match, we picked up those extra characters. So if we wanted to pull out just the match, we can add the -O option to grep. And here it makes it even clearer that we picked up the white spaces and punctuations. So in my earlier version of this slide, I said there's no way around this with grep. And I changed that, though, to say there's no easy way around this with grep. A more advanced topic that we're not going to get into today, with Perl-compatible regular expressions, we could do things called positive look ahead and positive look behind to look for the context and avoid those spaces the spaces and punctuation marks. But there's a much easier way to do this, and that is using word boundaries. So we can delimit the match with \less than and \greater than, or \b and \b to denote word boundaries. Also, if we're using grep, we could use the -w flagger option to select matches that form whole words. Now, all of these are going to work, but my preference is the first one, using the \less than and \greater than, since that's also going to work with grep and awk instead. And you can see if I use word boundaries, here I'm using, in the first case, backslash less than, looking for a string of exactly 5 digits, backslash greater than, that I get my 5 matches, and I didn't pick up any extra characters. I didn't get those spaces or the commas. And you can see using grep-ew that does the same thing. Okay, so I mentioned about 15 minutes ago that regular expressions are by default greedy, meaning that they look for the longest possible match. Lazy match, on the other hand, looks for the shortest possible match, and it's implemented in grep using the lazy quantifiers, question mark, plus question mark, star question mark, with the dash capital P option, which means Perl-compatible regular expression. So if we look on the left, looking A dot star B and lazy.text, we see we get these very long matches extending from the first capital A through the last capital B in that string. If I do a lazy match instead, here using Perl-compatible rather than extended regular expressions, A dot star question mark B, so we replace the star with star question mark, we get the lazy matches. So we look for the shortest possible matches of A followed by a string of characters followed by a B. And you'll notice in the first and the third lines, we actually return 2 matches. Okay, just a few more topics to get through. So, like just about everything else in the Linux world, special characters can be escaped with the backslash. If you forget the backslashes, the errors can be very subtle. So here I'm going to be looking for, I want to look for specifically the letter X preceded and followed by a string of characters enclosed by parentheses. So let's look at the first regular expression. Here I have parentheses, dot star, X, and then dot star after the X. And we see that we got some matches. We got those lines that contain an X, but we also picked up everything that was on either side. So those parentheses were just being interpreted in the context of meaning grouping. But if we wanted literal parentheses, we need to precede those with a backslash so that they no longer have the special meaning to grep. Same thing with the curly braces. Now in that third example, I haven't quite been able to figure out what is going on if I leave if I don't use the backslashes. So this is kind of an incorrect syntax. The curly braces should be enclosing an integer or an integer or a pair of integers. But in the last example, I used backslashes in front of those curly braces to escape their meaning. So now we can be looking for literal curly braces. So again, anytime you're trying to do a match involving any characters that would have special meaning to grep or to Linux, be sure to precede those with a backslash. Now, we're not going to get very deep into awk or sed today. I just have a couple of slides. I'm just putting these in here to show you that everything that we've covered so far today in the context of grep is also going to apply to awk. So if you're not familiar with awk, don't worry about this. But I do encourage you to go back and look at the Linux tools slides and presentation. So a awk command consists of awk followed and then in single quotes a pattern followed by an action and then list the files that it's going to operate on. So in the first case, we are going to print all of the lines that contain pair at the start or the end of the line. Again, here we're not really using the full power of awk. We're just replicating the capabilities of grep. And you see that we're going to get those 4 matches where a pair appears either at the beginning or the end of the line. The main difference compared to grep, though, is that the regular expression is going to be enclosed within within forward slashes. And the second example, we look for A followed by 3 or more B's followed by a C. And the same thing with sed. Sed supports regular expressions. Here again, we're just doing something very simple. We're replacing pair at the beginning or the end of the string with a series of 4 X's. Again, if you're not familiar with sed, don't worry too much about this. The takeaway is that everything that we learned about regular expressions with grep is also going to apply to sed. But like grep, the default is basic regular expression, so remember to use the -E option so that you can avoid having to escape special characters. And I show on the right, if I hadn't used -E, I would have to use a backslash in front of the vertical bar. So it gets a little confusing with the different flavors of regular expressions. And I've summarized it here, showing the default behavior in green. So for grep, we have basic, extended, and Perl-compatible regular expressions. For awk, we just have extended regular expressions, and for sed, we have basic and extended. So we didn't get too much into Perl-compatible regular expressions here. I think I'm going to expand that into another talk. It's really more advanced topics. We just saw one little taste, and that was lazy matching. You might be wondering why Perl-compatible regular expressions. I doubt that there are any Perl programmers here, but if you stick around at the end, I'd be curious to hear from any of you who did work with Perl. Perl is not nearly as popular as a programming language as it used to be, but what it was really known for was its handling of regular expressions, and it had a very extensive syntax that allowed you to do some really advanced things that we didn't cover here. Unfortunately, the Perl-compatible regular expressions that were only implemented in grep. Okay, so one more topic and then I'm going to be wrapping up. If you look in the directory user bin, you're normally going to see one awk, which is probably a symbolic link to gawk or GNU awk, one sed, and a whole bunch of different greps. Now, if we ignore the symbolic links and the original grep, we're left with the following. So that's these two columns on the left. We have BZ grep and E grep and F grep and on grep and message grep and P grep and so on. I'm going to say though that out of all of these, there's really just 2 that you need. So just use the basic grep with -E for extended regular expressions, or -F for fixed patterns, and that does everything that E grep and F grep do. They've been deprecated, but they're just carried along because some people are still using them in their scripts. XZ grep searches for patterns in files compressed using bzip2, gzip, lzma, and so on, and that covers the functionality of bz grep, ze grep, and so on. And then the other ones that we have here in blue are pretty much used by the Linux sysadmins. So just to show you that you can search for patterns in compressed files, this is something that I discovered relatively late in my career. I would take a file that was compressed, say using bz2 or gzip, and I would uncompress it, and then I would use grep. But you could use xz grep directly to do a regular expression search of these files. And the beautiful thing is, you could just use a single command for all of the different compression schemes. So xz grep will recognize from the file extension .bz2, .gz, and so on, what kind of file you're working with. All right, so the last thing, and I think it will wrap up right at the top of the hour. I would be surprised if anybody here has not used LLMs at some point. And you can use LLMs for writing regular expressions. But I'm going to tell you there are 2 reasons why you still want to know this material. So the first is that the LLM might not do exactly what you want it to do. So I asked ChatGPT, said, write a sed one-liner for me that replaces all instances of the string pair with 4x's, but only if it appears at the start and the end of the line. Now, if you look at the one-liner that I got, you will notice that for two of the substitution commands, it has a space after the pair, pair space, or a space before the pair. So this is a little slightly different from what I wanted. I asked for the string pair, not the word pair, separated by spaces or punctuation marks. So here again, it didn't do quite what I wanted to do. Second of all, sometimes it's just easier to write the regex yourself. So I said, write a grep one-liner that outputs all lines in a file that contain the pattern A, followed by exactly 2 or 3 occurrences of the string XYZ, followed by B. Here, ChatGPT did exactly what I wanted to do, but if you know how to use regexes, I think it would be easier just to write that out, just like you write math equations rather than spelling them out, using English. I won't go through all of this, but I would say read this slide on your own. This was ChatGPT's answer to the question. Since LLMs are so useful for writing regexes, why should I still study how to create them manually? And it actually gives a pretty good breakdown of all the reasons why you still want to understand regexes and be able to write them from hand. So here we are, right at the top of the hour. Going to wrap up, combined with tools such as awk, and grep, regexes give you a powerful way to search and manipulate text. Don't be overwhelmed by all the regex options. We covered a lot of material in 1 hour here. I'd say learn what you need to get started, then pick up the rest incrementally along the way. Be careful when using LLMs to help you construct regexes. They're not 100% reliable, and sometimes it's just hard to specify in words exactly what you want to do. And many programming languages, R, Python, Perl, C++, have regexes. Now, while the syntax may be different, all of the concepts that you learned here today are universal. And with that, I will stop sharing, and I am happy to answer any questions.